Okay, perfect. Thank you for the introduction. So welcome everybody. So indeed, I'll be talking about flexibility in power systems, and I'll be focusing on distribution systems and how the flexible resources that are present in distribution systems can also contribute to the system-wide flexibility needs. So in Pathfinder, we define flexibility as the ability of the energy system to manage variability in the electricity supply and demand, and we consider different timescales from very short to very long term. And this variability can be managed by adjusting the energy supply, conversion, demand, and storage, or imports, exports. Now, if we refine this a bit more to power systems, the definition that I quite like was from Hitachi, is the ability of power systems to cope with variability and uncertainty at all times. And if we specify a bit more and look at distribution systems, I would consider only the first two timescales, which is instantaneous and intraday or intra-week, because the seasonal storage requires large quantities of energy storage, and the resources required for this are typically less present in distribution systems. Second part that is very important for us is the concept of these distributed energy resources, which are the small-scale energy resources, such as PV or batteries, because these are really the resources that we talk about or that we have available within distribution systems, and of which we want to use the flexibility to provide services both within the distribution system and to the full bulk or the transmission power system. And then finally, we're talking about distribution systems, but we should talk about active distribution systems or active distribution networks, because distribution systems will refer to the old terminology where we really have the power that comes from the big power plants and that then flows downstream towards the end consumers with no active components within that network itself. While in new power systems, we have a lot of active elements, and the management of these active elements, which can be generation such as PV, batteries, or STATCOMs for reactive power compensation, are fully integrated in the operation and management of those systems. Now, we have much more of these distributed energy resources in our power systems, and the question is, how do they impact our system? And we'll see that this impact is a bit different on the distribution level than on the transmission level. On the transmission level, we have an increasing difficulty to balance demand and supply because there is mismatch between the moments where electricity is generated and when it is consumed. And this can lead to very high price volatility and then even going to negative electricity prices. And in these cases, we can have significant curtailment of renewable energy resources. It will also, and I will come back on this a bit later, lead to area or schedule balance violations. So this is on the transmission system, and this is typically represented by this duck curve, which Hitachi projects to look more like a canyon in 2030 if we see this trend continuing where we have more stochastic generation with especially a lot of PV production in the middle of the day and consumption that is still very important in the beginning and the end of the day. In distribution levels, next to these issues, we also have voltage rises that are due to reverse power flows, and typically these are mostly caused by PV productions. We also have voltage fluctuation, and because of higher electrification, for example, of heating, but also due to EVs, which are adopted much more and are expected to continue in the future, we have increasing peak demand, and this will lead to increasing load on the distribution system and possible congestions on lines and transformers. And also in these systems, we have increasing variability in local demand, which is exacerbated by the fact that all the resources are close geographically, and so they are prone to the same meteorological variations. Now, because we have different problems, we also have different needs. And so the needs we really have at the distribution, sure we manage the congestion as well, and also try to reduce the losses reduction, because the more current we have flowing through the lines, the more losses we will have, and we need to try to reduce this as much as possible. And on the transmission system, we have the balancing issues and the congestion management, and we will see how we can handle these issues also using the flexibility present in distribution system. Now, I said in distribution systems, we mostly have distributed energy resources available. And so which are these? And we can divide these in 4 categories. So we have the generation assets, which are typically PV. In Switzerland, it will be mostly PV, but also a little bit of wind. And these can be operated in a flexible way through curtailment or by controlling their voltage or their reactive power injections. Then we have the demand, and we have higher electrification, which also means we have a higher portion of the demand that is potentially flexible. So EVs and heating are very good examples of demand that we can play with. And then we have more storage elements, such as batteries. And then we also have the traditional devices used for network operations, such as StatComs, tap changing transformers, and now, depending on what we need to manage in the distribution system, we will have a different control scheme. And typically, all these control schemes will be happening simultaneously with different devices active more for different services. Okay, voltage control, for example, will typically be done by voltage regulation devices or shunt converter. Similarly, for the reactive power compensation. And then when we have larger assets, such as batteries, we can go towards real economic and technical optimization within this distribution grid, where the goal can be to minimize electricity costs, but also to make sure there are no congestions, to make sure that all the users can access the power that they require, and so on. Now, this is how we use the flexibility and we operate the distributed system by itself. So the last part, so basically to summarize what I was saying about this slide is that in this case, they were using the battery and allocating part of the capacity for the management of the distribution system. So for the self-management, because we consider this is the operator of the distribution system. And then the remaining capacity, which was estimated based on forecasts, so how much capacity they needed, could then be bid or ancillary services at the transmission level. And in this specific case, it was primary frequency regulation. And so what you can see on the figure on the bottom right is that based on the frequency deviations, on the upper curve, you can see the power contributions of the battery in red and in blue. And so there is a portion that is used for the self-management and a portion that is used to provide a frequency service. Now, so we show that we can, in some cases, use flexibility from the distribution system to the transmission system because there is a surplus of flexibility available at the distribution system. But do we really need this? And so for this, I refer to a presentation given by StratGrid 2 weeks ago at their balance group manager partner meeting, where basically they show the issues that they're having currently with the model where balancing groups are used to reduce the imbalance at the transmission system in an attempt to reduce also the reserve requirements in the wholesale flexibility market. And so what they show is that when each balancing group is simply trying to adhere to their schedule that they define in the day ahead, they have a significant amount of imbalances and that this number of imbalances is increasing over the last year and a half. Now, what StratGrid reports about this is that these imbalances happen more frequently recently. They also happen more frequently at weekends. And one possible issue is that the schedule is made in the day ahead. And so in real time, there is a lack of compensation, of flexibility available to compensate for the short variations. They also say, or they show basically for the high injections of PV, that a small portion of the energy provided by these PVs is causing a large part of the power problems. And they recommend to manage these power peaks locally. And so this is really where this interaction between distribution systems and transmission systems will become important, because part of the flexibility also for the bulk balancing can be provided by the distribution system and part of it by the transmission system. So as said, we need coordination between this TSO and DSO to allow this flexibility to be shared and to be used in the best way. And to leverage really this flexibility that is present at the distribution system and show its availability to both the DSO and the TSO, there are multiple approaches. And in the next slides, I will basically highlight two approaches. And for each approach, I will show some work that is being done at the lab at EPFL by myself or by colleagues. And so the first approach is really to go into market-based methods where we look at local flexibility markets or local energy markets. So where in the similar way as the wholesale market at the transmission level, we have also market at the distribution level. And the second set of approaches is more of a control-based method. And the method I will introduce is a sort of virtual power plant method, which means we're going to aggregate the flexibility present at the distribution level and then show the aggregated flexibility from the distribution system to the transmission system operator or to people interested in acquiring this flexibility for use at the transmission level. So first, for the market approach, so it's somehow similar to a wholesale market, and I'll introduce just briefly the different actors that we would have in such a local flexibility markets. And there are two actors, so the DSO, so the distribution system operator, and the BRP, so a balance responsible party, so someone who would manage such a balancing group. which has to maintain a schedule at the transmission level. And these would be actors that might be interested in acquiring flexibility from distributed energy resources. So they would be sending offers to a local flexibility market operator to acquire flexibility according to their needs. And so what's interesting here is that both actors at the distribution level and the transmission level could bid for the same flexibility in a common market. And then you would have different actors, such as aggregators, which bring together different prosumers, which have access to these distributed energy resources, and which bid their capacity in this market. Now, then for how this market works, there are different mechanisms that are possible. So it could be operated by a responsible operator, which gets the information of the participants and then maximize the social welfare by activating the flexibility that is required and allocating it to the users that need it. Or it could be based on bids where actors maximize their own benefit and then bid what they want to offer in the market or what they need in the market. And some work that was done by a colleague of mine was looking at how do we extend distribution levels, or how do we reinforce distribution systems to allow such a market to take place. And in this specific case, we're not looking at copper reinforcements, but we're looking at reinforcement of the system through the installation of battery energy storage systems. And the question was, well, where and how much battery energy storage systems should we install so that we have a market where all the different players can play a fair game? Because in distribution systems nowadays, you have more and more congestions, and you have places where it's harder to install PVs. So not every owner of distributed energy resource will have the same access to this market. And so we try to install these reinforcements in order to level the playing field for the different players. Basically, so the second option, so I introduced the market approach to provide flexibility from the distribution system. The other approach would be a more centralized approach where we control the distribution system in a more centralized way. And in this case, the approach introduced is the approach is a virtual power plant. So where we aggregate the capability of the different energy resources and represent it as a single entity. And so if we start from one single distributed energy resource, we can have a capability curve, such as present on the bottom right, which shows the power capacity in reactive and active power that this resource could offer at a certain time. Then if we have a system that is not at all congested, so over-dimensioned, or if we have an energy hub, we can get a Minkowski sum, and we get the aggregate capacity. But when we have binding grid constraints, this problem becomes more difficult, and especially when we have a lot of uncertain production or consumption within our network, these constraints will become stochastic, and we get a problem that is not that easy to solve. And typically, we want to make sure that if we offer some flexibility, we can also provide it with a very high probability. And so typically we formulate such a problem in a robust way, saying that we determine the power capabilities that we can guarantee for any uncertain realization. And then we want to account for the capabilities of individual resources, grid constraints, and uncertainty. Problem is that mathematically this becomes a hard problem because we're producing a high-dimensional polytope on a subset, and this will become intractable very quickly. And so we would use approximate feasibility sets, such as hyperboxes, ellipsoids, to obtain a simplified capability curve of our distribution systems, which represents basically this distribution system as if it was a single power plant, which can then offer flexibility at the transmission level. And what we're working on now is to expand this idea to a virtual power plant that can offer multiple services. So, for example, you could consider primary frequency regulation and secondary frequency regulation. And we can then bid capacity for these different services depending on forecasts of the service price to optimize or to maximize the value of flexibility that this distribution system can offer. An advantage of such an approach is obviously that the grid constraints of the distribution system are handled internally in this optimization problem, so that any flexibility bid that is chosen by a transmission operator or by a balance responsible party at the transmission level will not lead to problems at the distribution level. And also an extension that we're looking into is to try to reduce conservatism by not necessarily considering a robust uncertainty set, but by considering this in a probabilistic way, so allowing a small probability that we are not able to provide the full flexibility to ensure that we have a larger solution space. And I'll come back a bit to this later, how this fits in potential future evolutions of flexibility markets. Now, so this may sound a bit theoretical, but actually there are already real examples of flexibility from such distributed energy resources that are used to provide system-wide balancing services. And I'll just mention briefly two here. The first one is the Tesla virtual power plant in the ERCOT system with the ERCOT system operator in America. And so here we have an 80 megawatt pilot project, so it's really quite big, which consists of aggregators that bid the capacity of individual owners, so people who have a Tesla or a Tesla Powerwall or controllable loads, and who decide that part of their capacity can be bid in this flexibility market. Of course, they are paid for this. And so this is now working, but the challenge that ERCOT has is to make sure that information on the individual injections that are part of this aggregated capacity are mapped well so that they can see how this is going to affect the grid also at the distribution level. A second example, which is maybe more familiar because it's closer to Europe, is the Equigi, which is a balancing crowd balancing platform. And the idea here is really to assemble offers and demands for flexibility, also from small users, to couple demand and supply for flexibility that can come also from the distribution system. And here there are also a series of pilot projects, for example, for frequency regulation in the Netherlands. Now, so these are methods that exist, that are looked into, and that are also already being implemented, at least in testing projects. How might this look in the future? And for this, I took one example or one evolution that is happening right now in the Nordics, where Energinet, so the system operator in Denmark, allows for probabilistic ancillary service bids. And they call this the P90 requirement because it means that someone who bids a certain capacity for an ancillary services has to guarantee that this will be, or that they can provide the full capacity in at least 90% of the cases. And what this means is basically that they open the flexibility markets also to stochastic energy resources. So for example, a PV power plant where they can have an idea of how much they will produce and how much they can shift up and down, but they cannot be exactly certain. And this in turn then allows to bid more, or to make more capacity available for bidding into these markets, which allows us to access a larger pool of distributed energy resources, which can potentially offer flexibility when older power plants, which are now still in place, but which might be displaced when we have even more solar PV, are getting out of the system. And one of the papers cited below, so from Gada Peter, shows how they can apply this P90 requirement to aggregate the flexibility of EVs for grid service provision, as an example. So, to conclude, there is a very large flexibility potential at the distribution level, and this is expected to increase because you have more EVs, more PVs, and we will also have more need for it because there will be less flexibility directly connected at the transmission level. We need coordination to be able to use this flexibility in a correct way so that we can help the transmission system without neglecting the distribution system. And this coordination needs to be between the system operators, but also between the system operators and aggregators and individual prosumers. And for all the rest to work, there need to be good communication platforms so that the bids and the demands can be coupled. And also, the better the forecasts for both demand and production are, the better we will know which flexibility capacity is available and where it will need it. So in the same way as our Pathfinder machine consists of a lot of different elements that need to work together, here we see that to leverage this flexibility from distribution or distributed energy resources and use it both in the distribution system and the transmission system, all these little parts need to come together, and that is happening already, but there need to be some incentives and platforms put in place to allow this to be used to the fullest. So that's where I would like to end this talk. I'm happy to answer any questions now, and else you can always contact me at the email address on the slide. Thank you.